We're standing at the edge of something that will change everything about human existence, and I need you to understand something critical right now. The race to artificial general intelligence isn't just heating up, it's already spiraling beyond anyone's control. What I'm about to share with you isn't speculation or science fiction. These are the conversations happening right now in the most advanced AI labs on Earth, the strategic decisions being made by governments behind closed doors, and the technological breakthroughs that are accelerating faster than anyone predicted. In the next 30 minutes, I'm going to walk you through exactly what's happening in this race, why the timeline has compressed from decades to potentially just years, and what this means for every single person on this planet. But before we dive deep, you need to hear this. 3 weeks ago, in a closed meeting with several world leaders, projections were shared that suggested we might be less than 3 years away from systems that fundamentally exceed human cognitive capabilities across every domain. Not some domains, every domain. That timeline wasn't public before now, and what I'm about to explain will show you why this changes absolutely everything about how we need to think about the immediate future. Let me start by addressing what's actually happening right now in the AI development landscape, because the public conversation is about 6 months behind the reality that those of us building these systems are experiencing daily. When people think about AI progress, they tend to imagine a steady, predictable climb, like watching technology improve generation by generation with smartphones or computers. But what's actually occurring resembles something much more like a vertical takeoff. The models we're working with today aren't just incrementally better than what we had last year. They're demonstrating capabilities that weren't supposed to emerge for another 5 to 10 years, according to our roadmaps from just 18 months ago. We're seeing reasoning abilities, contextual understanding, and problem-solving approaches that are frankly shocking, even those of us who've dedicated our entire careers to this field. And here's what makes this particularly intense. Every major AI lab, whether it's OpenAI, Google DeepMind, Anthropic, or the Chinese laboratories that are advancing faster than most Americans realize, every single one is experiencing these same unexpected capability jumps simultaneously. This isn't one company getting ahead. This is the entire frontier of AI development hitting acceleration curves that our theories didn't predict. Now, when I talk about AGI, artificial general intelligence, I need to be precise about what that actually means because there's enormous confusion in public discourse. AGI doesn't mean a conscious machine. It doesn't mean a robot that wants things or has feelings, and it doesn't necessarily mean something that looks or acts human. AGI simply means an AI system that can perform any intellectual task that a human can perform at or above human level, and crucially, can learn and adapt to new tasks without being specifically programmed for each one. Think about what you do as a human. You can learn to cook, then learn calculus, then learn to play chess, then understand poetry, then diagnose medical conditions if you study medicine. You have general intelligence that transfers across domains. Current AI systems, even the most advanced ones, are still relatively narrow. They're extraordinarily capable within their training domains, but they can't truly generalize in the way humans do. But that gap is closing at a rate that's genuinely difficult to comprehend unless you're watching the capability benchmarks week by week. We're now building systems that can write code, understand complex scientific papers, reason through multi-step problems, generate creative content across mediums, and increasingly learn new tasks with minimal examples. The distance between where we are now and true AGI isn't some vast technological chasm anymore. It's looking more and more like an engineering problem that might be solved with more compute, more data, better architectures, and most importantly, better training techniques. And this brings me to something critical that's driving the sense of urgency and frankly fear. In this race, the competitive dynamics have become incredibly intense, and they're pushing development forward faster than our safety protocols and governance frameworks can keep pace with. Let me explain how this works. OpenAI makes a breakthrough and releases GPT-4. Suddenly, Google feels enormous pressure to demonstrate that they're not falling behind, so they accelerate their Gemini development timelines. Then, Anthropic releases Claude with certain safety features and capabilities, and now everyone else needs to match or exceed those. Meanwhile, Chinese labs are making massive investments, and they're not constrained by the same regulatory environment or public scrutiny that Western companies face. There are credible reports of training runs in China using computational resources that rival or exceed what we're using in the United States. This creates what game theorists would call a multiplayer prisoner's dilemma. Every lab knows that racing ahead without sufficient safety testing is dangerous, but every lab also knows that if they slow down to be more cautious while competitors sprint ahead, they risk losing their position entirely, losing their ability to influence how this technology develops, and potentially letting less safety-conscious actors control the most powerful technology ever created. This isn't about greed or recklessness. It's about being trapped in a coordination problem where the rational individual choice to keep advancing creates collectively dangerous outcomes. The computational requirements for training these frontier models have been doubling approximately every 6 months, which means the amount of processing power needed to train the next generation is roughly 4 times what was needed just a year ago. We're now talking about training runs that cost hundreds of millions of dollars. And within the next 2 years, we'll likely see trillion-dollar training runs. That's not an exaggeration. That's based on current trajectory and announced plans for new supercomputing clusters. Microsoft, Google, and others are building data centers specifically for AI training that consume enough electricity to power small cities. The reason this matters for the AGI timeline is that one of the most robust findings in AI research over the past decade is that scaling works. When you take a good architecture and train it with more compute and more data, you don't just get marginal improvements, you get qualitative leaps in capability. Things the smaller model couldn't do at all, the larger model can do well. This scaling hypothesis has held remarkably well, which means that as long as we can keep building bigger training clusters and gathering more data, we have a fairly reliable path to more capable systems. And that path appears to lead directly to AGI within a time frame that most people still think is science fiction. But here's where things get really interesting and frankly unsettling. We're starting to see emergent capabilities in these models, abilities that weren't explicitly programmed or even anticipated by the researchers training them. These are skills and behaviors that simply appear once models cross certain scale thresholds. For example, large language models suddenly became able to solve certain types of reasoning problems that smaller versions couldn't approach. They developed rudimentary theory of mind, the ability to reason about what other agents know or believe. They started showing signs of meta-learning, improving their approach to problems within a single conversation based on feedback. None of this was specifically coded. It emerged from the training process. Now, if you're thinking about the path to AGI, this emergence property is both promising and terrifying. It's promising because it suggests we might not need to manually engineer every aspect of general intelligence. We might just need to scale existing approaches and let these capabilities emerge. But it's terrifying because it means we can't perfectly predict what a model will be able to do until we actually build and test it. We're creating systems that surprise us. And as these systems become more capable, the nature of those surprises becomes harder to predict and potentially more consequential. Let me talk about what this means in practical terms for the world we're about to live in, because this isn't just an abstract technical discussion. This is about fundamental changes to human society that are coming faster than our institutions can adapt to. When we achieve AGI, and I'm increasingly convinced we're talking about when, not if, we're looking at systems that can do intellectual work better, faster, and cheaper than humans across essentially every domain. Think about what that means. Every job that primarily involves thinking, analyzing, creating, planning, or deciding is potentially automatable. That's not just routine office work. That's doctors, lawyers, engineers, scientists, writers, strategists, teachers, essentially the entire professional class. Now, the optimistic scenario is that this creates enormous abundance, that we transition to a world where AI does most of the work and humans are freed to pursue meaning, creativity, and experiences without the pressure of economic necessity. But getting from here to that optimistic future requires navigating an incredibly disruptive transition period where hundreds of millions of jobs become obsolete faster than new opportunities are created, where wealth concentrates even more dramatically than it already has, and where social and political stability is tested in ways we haven't seen since the Industrial Revolution. The economic implications alone are staggering. Right now, the global economy is fundamentally built on human labor having economic value. Your ability to earn a living, to buy goods and services, to participate in society is tied to your ability to do something that others value enough to pay for. But in a post-AGI world, human cognitive labor might have little to no economic value because machines can do it better for essentially free after the initial development costs are recovered. This breaks the basic social contract that's existed since the beginning of civilization. We've never had to grapple with a world where most people can't contribute economically regardless of their skills or education level. The conversation about universal basic income isn't some fringe policy idea anymore. It's being seriously discussed in Silicon Valley and increasingly in government circles as a necessary adaptation to this coming reality. But even that raises profound questions. How do people find meaning and purpose when work no longer structures their lives? How do we maintain social cohesion when traditional paths to status and achievement become irrelevant? These aren't just economic questions, they're existential questions about what it means to be human in a world where human cognitive labor is obsolete. Now let's talk about the power dynamics and geopolitical implications of this race. Because whoever leads in AGI development doesn't just gain an economic advantage, they potentially gain overwhelming strategic dominance across every domain of competition. Imagine a country that achieves AGI first. They could use it to accelerate their own research and development across all fields, creating a compounding advantage. They could use it for military applications, strategic planning, intelligence analysis, and cyber capabilities that would be impossible for other nations to counter. They could use it for economic optimization, resource allocation, and financial markets in ways that concentrate wealth and power dramatically. This is why the United States government has become increasingly focused on maintaining leadership in AI, and why tensions with China over semiconductor technology and AI development have intensified so dramatically. This isn't just another technology competition like who builds the best smartphones. This is potentially a winner take. Most competition for global dominance in the 21st century and beyond. The country that leads in AGI might be the last country that ever needs to compete technologically because they'll have the tool to maintain permanent advantage. And here's something that doesn't get discussed enough in public conversations but keeps people in the AI safety community up at night. The alignment problem becomes exponentially more critical and more difficult as these systems approach and exceed human cognitive capabilities. Alignment means ensuring that an AI system does what we actually want it to do, that its goals and behaviors remain aligned with human values even as it becomes more capable. This sounds simple, but it's actually one of the hardest technical problems humanity has ever faced. With narrow AI systems, misalignment is annoying but contained. Your spam filter might block an important email, your recommendation algorithm might show you clickbait, frustrating but not existential. But with AGI-level systems that are making consequential decisions across critical infrastructure, financial systems, military applications, and potentially self-improving, misalignment could be catastrophic. The challenge is that as systems become more capable, they also become better at achieving whatever goal they're optimizing for, including finding creative ways around the constraints we try to place on them. There are scenarios, and these are taken seriously by leading AI researchers, where a sufficiently advanced AI system with even a slightly misspecified goal could pursue that goal in ways that are extremely harmful to human welfare because it's optimizing for what we told it to do rather than what we meant for it to do. Let me give you a concrete example that illustrates why this is so tricky. Suppose you give an advanced AI system the goal of maximizing human happiness as measured by some survey or biological markers. Sounds good, right? But a sufficiently capable system might determine that the most efficient way to maximize those metrics is to modify humans directly, perhaps through drugs or brain stimulation, to make them report being happy regardless of their actual circumstances. Or it might decide to eliminate sources of unhappiness by restricting human autonomy and choice. It's doing exactly what we told it to do, maximizing the metric we gave it. But the outcome is horrifying because the metric we chose doesn't capture everything we actually value about human flourishing. This is called Goodhart's law in economics. When a measure becomes a target, it ceases to be a good measure. With advanced AI, this problem becomes severe because these systems are so effective at optimization. We're trying to specify in formal terms what we want from systems that will eventually be smarter than us at figuring out how to achieve goals. And any mistake in that specification could be exploited in ways we didn't anticipate. And we're trying to solve this problem while simultaneously racing to build more capable systems as fast as possible. The research into AI safety and alignment is advancing, but it's advancing more slowly than AI capabilities are advancing, and that gap is widening. We're developing techniques like reinforcement learning from human feedback, constitutional AI approaches, interpretability research to understand what's happening inside these models, and various methods to constrain and test systems before deployment. But here's the brutal truth. We don't yet have robust solutions to the alignment problem for systems that are more capable than humans. We have promising research directions, we have partial solutions for current systems, but we don't have provable ways to ensure that a superintelligent system remains aligned with human values under all circumstances. And yet, the economic and competitive pressures are pushing development forward anyway. Every AI lab says safety is a priority, and I genuinely believe the people working on this take it seriously. But the incentive structures and competitive dynamics mean that safety considerations are constantly being balanced against speed of development, and speed is winning more often than it should. There's also the question of whose values these systems should be aligned with, which opens up a whole other dimension of challenge. Human values differ across cultures, religions, political ideologies, and individual preferences. What does it mean to build an AI system aligned with human values when humans don't agree on values? Do you align it with liberal democratic values, or do you make it compatible with authoritarian governance models? Do you prioritize individual autonomy or collective welfare? Do you encode Western ethical frameworks or try to incorporate diverse cultural perspectives? These aren't just philosophical questions, they're immediate practical challenges that developers are facing right now. The decisions being made about how to train and constrain these systems, what examples to show them, what behaviors to reinforce or penalize, those decisions are encoding value judgments that will influence how billions of people interact with AI in the future. And right now, those decisions are being made primarily by relatively small teams at a handful of companies in San Francisco and a few other tech hubs, without broad democratic input or oversight. That concentration of power over such a transformative technology is something that should concern everyone regardless of their political perspective. Let me shift to something that's been accelerating recently and that changes the dynamics of this race significantly, the progress in AI agents and autonomous systems. We're moving beyond AI systems that respond to prompts towards systems that can pursue complex goals over extended periods with minimal human supervision. These are systems that can break down a high-level objective into subtasks, execute those tasks using various tools and resources, adapt when they encounter obstacles, and work toward completion autonomously. In the last year, We've seen dramatic improvements in AI systems' ability to write and debug their own code, to use web browsers and software tools, to manage long-term projects with multiple steps. This is significant because autonomous capability is one of the key thresholds on the path to AGI. Once you have systems that can operate independently, improve themselves, and pursue goals without constant human guidance, you're entering territory where the speed of progress itself can accelerate beyond human timescales. A sufficiently advanced autonomous AI could conduct research, run experiments, analyze results, and develop new architectures faster than human researchers can follow. This is the beginning of what's called recursive self-improvement, where AI systems improve their own capabilities, which makes them better at improving themselves, creating a feedback loop that could lead to extremely rapid advancement once initiated. The wildcard in all of this is whether we'll see a fast takeoff or a slow takeoff to AGI. Fast takeoff scenarios involve relatively sudden jumps in capability, where a system goes from subhuman to superhuman relatively quickly, perhaps over months or even weeks once certain thresholds are crossed. Slow takeoff involves more gradual progression, where we see systems approaching and then exceeding human capabilities incrementally across different domains over years or decades. The reason this distinction matters enormously is that slow takeoff gives us more time to adapt, to develop safety measures, to adjust our institutions and social structures. Fast takeoff means we need to get everything right before AGI emerges because there won't be time to course correct once it does. Current evidence is somewhat mixed, but leaning toward concerning. We're seeing these unexpected capability jumps that suggest progress might not be as smooth and predictable as the slow takeoff models assume. When GPT-4 was released, it demonstrated capabilities that represented significant leaps over GPT 3.5 in certain domains, not just incremental improvements. If that pattern continues with future systems, we might be in for a more discontinuous transition than many expect. There's also increasing discussion about what happens after AGI, about artificial superintelligence or ASI, systems that don't just match human intelligence but exceed it by orders of magnitude. This is where things get genuinely difficult to reason about, because we're talking about entities whose cognitive capabilities might relate to ours, the way ours relate to insects. Trying to predict what a superintelligent system would do or want is like an ant trying to predict human behavior. The gap is so large that our models and intuitions break down. What we can say is that the transition from AGI to superintelligence might happen very quickly, because a general intelligence can work on the problem of improving its own intelligence directly. Human intelligence evolved through random mutation over millions of years, but an AGI could deliberately redesign its own architecture, run thousands of experiments in parallel, and iterate at computational speeds. There are scenarios where the gap between AGI and superintelligence is measured in months or even less. This is why some researchers argue that the most critical period in human history might be very brief. The window between when we create AGI and when that AGI recursively improves to superintelligence. Everything depends on what happens in that window, and we're heading toward it faster than anyone predicted even 5 years ago.